All right, so as you've been filling this in, really it's tons of patterns. And you can see lots of different patterns. You can remember it different ways. But there's really just one thing, at least for me, that I memorize, and everything else is just knowing facts about it. The one that I always memorize is that sine of 30 degrees is a half. If I know that one fact, I can fill in a whole bunch of other stuff. Because what always goes with a half? Root 3 over 2. And so I know that if sine there is a half, the cosine is root 3 over 2. But that pair, it holds up in other ways as well. So like if sine of 30 is a half, and I want to find the sine of 60, again, that same relationship holds. So if this one is 1/2, the other one is going to be root 3 over 2. And of course, if that is root 3 over 2, then its partner has to be a half. And that's at 60 degrees. And of course, knowing those, remember that the ones that are aligned horizontally and vertically will have the same coordinates. So like these two are going to have the same y coordinate. That's the same sine then. And so we can know then that this sine is going to be root 3 over 2. And of course, if the sine is root 3 over 2, then the cosine must be a half. Just remember though, when we jump quadrants, we got to pay attention to how the signs might change. You notice that since we are now going to the left instead of the right, my cosines are now negative, because remember, cosine is your x coordinate. And so then we can start filling in lots of information like that. Now, something I have skipped over here is this one. That's at 45 degrees. What are both sine and cosine at 45 degrees? Yep, square root of 2 over 2. And they're both the same at the 45s. The one other piece here that we haven't dealt with is the horizontals and verticals. Remember, those are always ones and zeros because they're on the total outside of the circle. Like in this case, when we're at 0 degrees, we are not going up at all. That means our sine is 0, but we are going over. We're going over in the positive direction. Therefore, cosine is a positive 1. And we can get all the other horizontals and verticals the same way. Like if I go straight up to 90 degrees, notice I am going up, so sine is 1 there, but I'm not going over at all, so cosine is 0. Those thought processes are what we use to be able to fill in all of these different values. Now, of course, you'll see other patterns that you can use to fill it in, and that's great. But the overall picture needs to end up the same. So go ahead and check this, make sure everything is filled in correctly on this one, because we want every piece of notes to be correct. Pay special attention as you check it to the signs, that is the positives and negatives. Right, and so focusing on each quadrant and what they gave us within each quadrant. So here in our first quadrant, notice everything's positive, because right is positive for your x-coordinate, up is positive for your y-coordinate. Remember, cosine is x, sine is y. That's a fact that we know separately from this, but allows us to help fill this in, right? When I then go over to the second quadrant, we're going left and up. Left means a negative x value. Therefore, all of my cosines are negative over here in the second quadrant. I'm going up, so y is positive. That means all of your sines are positive then. When we then go into the third quadrant from there, we're going left and down. Left and down means both of them are negative. So you notice all of your points here, all of your sines and cosine values, down here in the third quadrant, make sure you do have them all labeled correctly as negative. And then finally, when we go over to the fourth quadrant, we're headed to the right, so x is positive, so your cosines are all positive, but we're going down. Down is y, y is sine. So all of your sine values here are negative for that reason. So yesterday we added some tools to our work here. We stopped looking at angles just as degrees. We also saw how we can measure angles as radians and what radian measures really mean and how they work. So we're going to take a little bit of time here today and convert each of these angles into the other. So take each of your degrees, convert them into radians, please. take all of your radians, convert those into degrees. Now let's check in and make sure you're heading in the right direction. Based on our notes that we took yesterday, we got a formula for doing these, and it's the same formula no matter which direction you're going. Hopefully you're using this. D over 360 equals R over 2 pi. Now remember how you can know what this formula is? Notice it's the full circle in degrees, 360 degrees in a circle. So we take the degrees over 360. And there's 2 pi radians in a circle. So it's over 2 pi. Both of them are over the complete circle when it comes to setting this up. And it's just a matter of if you know the degrees, you plug that in for D. Or if you know the radians, you plug it in for R. Solve for the other one. So continue solving through these 4 problems, and we'll take a look at the work here in just a few moments, at least for the first pair. All right, so for the first one, 780 degrees. I know that that is the degrees, so I plug it in for D. That one has to be in the same fraction with the degrees. That's another way to remember. So we do 780 over 360. Yes, it's more than a full circle around, but that's okay. We can still do it. Then that equals R over 2 pi. We're going to be solving for R here. Now, of course, we're going to cross multiply. So we're going to do 360 times R. That, of course, is just 360R. And then we're going to do 780 times 2 pi. Now, remember when doing 780 times 2 pi? I'm going to leave the pi in there. So I'm going to call that 1560 pi. I don't want to calculate it out as a decimal with the pi multiplied in. That's going to throw things off. All right? From here, I now need to get rid of the 360 on the left so I can get R by itself. So we're going to divide both sides by 360. Now with the start, that just gives me 1560 pi over 360. Now I don't want to do just 1560 divided by 360 unless I'm looking to see if it's a whole number. Because if it's a whole number, of course, it makes life easy. But in this case, it is not a whole number. So I want to treat this just as any other fraction that I would be working with. I'm just ignoring the pi for the time being, and I want to reduce that fraction. So we're looking to see what can we divide everything on both top and bottom by. As you're looking to see what you can divide them both by, of course, you'll notice they both end in 0. So we could start by making it just 156 over 36. That can make it easier. And then maybe you try dividing by 6. Yes, it is divisible by 6. If you did that, you'd find you could still divide it by 2. It does break down quite a ways. The biggest number was actually 120 that you could divide them all by. Do I expect you to just look at it and know that? No, you're probably going to reduce it in phases. But when we reduce it down then, that leaves a 13 pi on the top. Remember, the pi is just hanging out there. And a 3 on the bottom. So whether you reduce it in stages or all at once, you should still end up with that as your final answer. Notice now that does not reduce at all. So that is how I know it's the final answer. That's how I know I stopped there. So 13/3. All right, next one. We're going to go over to our radians, the 11 pi over 6. And we're going to be solving this one out. Now, we want the degrees, so it's going to stay a D over 360. The 11 pi over 6 is all over 2 pi. And so this is where we're going to cross multiply now. Now, of course, doing the D times 2 pi is hopefully fairly straightforward. That's just going to give me 2 pi D. But then for cross multiplying the other way, notice I'm multiplying 360 by 11 pi over 6. In order to do that, I'm going to be doing 360 times the 11 first. When I do that, that gives me 3,960 pi over the 6, because I haven't dealt with the 6 yet. Now, if this is going to work out really nicely for us, I can actually just divide 3,960 now by 6. And it does divide nice and evenly. And so when we do that, that just gives me 660 pi. If it didn't divide evenly, we'd just reduce it as much as we could to make our life simpler from there. All right, now I still want to get d by itself. So I'm going to divide both sides by 2 pi. And again, remember, the beautiful thing about having left pi in this whole time is that those pi's are just going to cancel each other out. And so really I'm just doing 660 divided by 2. So d equals 330. Now, of course, this is what d equals, right? d is degrees. So yes, I need to include the degree symbol on that. Remember, if we leave off the degree symbol, we're saying it's radians. In order to say it's degrees, you have to include the degrees. Now, having done these, of course, you did a lot of practice with doing these sorts of conversions on last night's homework. Remember last night's homework, you were going through the trig table and you were taking all of our degree measures and turning them into radians. So let's check each of those answers. So please, check that your table is now 100% correct. All right, now, having figured out all of these values, I expect you to be able to figure out and fill in all of these values without having to check your notes. In fact, in about a week and a half from now, we're going to have a test on these sorts of problems that we've been doing. And everything in this table is going to be on that test. And of course, test means no notes. So you're going to have to be able to do this. And I don't want you having to go through and do all of those same calculations that you did here over again. Because some of these come up so often that we really should know them. And there are some patterns, like we've talked about patterns with the degrees and with sine, cosine, and tangent on how we can know those things. And yes, there are patterns with the radians as well, but they're a little bit harder to observe ourselves at first. But I'm going to show you some tricks on how we can actually see them jump out at us a little bit more. And really it goes back to the same ideas as what we saw when we did our degrees. Like remember with degrees, we saw that we're just counting up by 30s as we went along here. So notice for all of these angles, all I'm doing is adding 30 degrees, right? In this case, we can see the same thing happening. What is 30 degrees in radians? We can see it up here, right? It's pi over 6. That one is worth memorizing. But like so many things, like memorizing that sine is 1/2, if you know that one thing, you're going to be able to figure out a whole lot of others. Because when I went up by 30 degrees, I just added 30, right? Well, I'm going to add another pi over 6 to that. That would be 2 pi over 6. What does 2 pi over 6 reduce to? Pi over 3. Really, every 30 degrees means I'm counting up by another pi over 6. So this was really a 1 pi over 6, 2 pi over 6. Then after that, oops, this one should also be highlighted there just for the consistency. Next after that would be 3 pi over 6, which you'll notice then I could reduce, pi over 2. Then 4 pi over 6, 5 pi over 6. Are you noticing the pattern here? I'm just counting up by pi over 6 increments, and I can just keep doing that throughout the entire table or even the entire picture in order to be able to figure that out. It's just that when I go to take these values and put them up into the actual radian, I just finish reducing it. But by knowing just this one value, we were able to figure out all of those other ones without having to do all the calculations again. This is a good thing. It saves us a lot of extra work just by knowing that I can count by pi over 6, just like I count by 30. And you can use that for other things too. Like you'll notice this didn't help me find the 45 degree increments. But I can still use the same kind of reasoning for the 45s. So 45 increments, so if I count by 45s, notice I'm at all of these angles. Well, what's 45 degrees in radians? Pi over 4. That one's also worth memorizing. So I know this one is pi over 4, but now that I know that, every 45 degrees I can count by pi over 4s. So if that's pi over 4, this would be 2 pi over 4. Then we go to 3 pi over 4, 4 pi over 4. You're noticing the pattern, right? And of course, if I wanted to know the actual value here, so 4 pi over 4, that just reduces down to be pi. And I could get that same thing if I called it 6 pi over 6, right? 6 pi over 6 equals pi. These just give us ways that by counting it out, we save ourselves from having to redo the big long formula. Now, can you still do the big long formula? Absolutely. But do you have to? I hope you don't have to. Now, the table, for some of you, this is like, oh, okay, that makes total sense. But for some of you, you're much more visual. So the picture might be a better way to be able to see it. So I want to kind of go through the same idea as we look at this pictorially as well. We know where 30 degrees is. Of course, we practice that a lot, right? Now, let's see if you have it memorized. Do you remember what the radian equivalent is for 30 degrees? It is pi over 6. Now that I know that is pi over 6, I'm going to go and fill in everything in this picture that would tell me. Now notice I'm not giving you this picture this time, just kind of letting you figure it out. Here in a minute, I'm going to give you another picture that looks kind of like this, actually with some more on it, and we'll see how much you can fill in on your own at that point. But for now, I know this pi over 6, and I want to see what all that tells me. Well, I'm going to go over another 30 degrees, which will bring me to another pi over 6, so I'm going to call that 2 pi over 6. And then if I go past that, that would be 3 pi over 6, 4 pi over 6. So you notice I can just keep filling this in all the way around my picture. 6 pi over 6. Now, of course, this isn't letting me fill in everything, is it? This isn't letting me fill in the 45 degree increments, which is why I said that one is worth memorizing and why it's worth actually knowing that one as its own pattern as well. So I went through just filling in, counting pi over 6s. Now some of them aren't reduced at the moment. Well, some of you are going to feel comfortable enough where you're going to reduce as you go and just follow that pattern. If that's the case, that's fine. That's great. If not, write it this way first and then go back and do the reducing. Either way is going to work. All right, now I do want to go ahead and put in the 45 degree increment as well. So let's see if you have it memorized here. What is the radian value, the radian equivalent for 45 degrees?
Pi over 4?
Yep, pi over 4. Knowing that, I'm now going to go ahead and fill in everything that could tell me, including some of them that I've already put in. Just going to see how I would have done it this way. So pi over 4. This would be 2 pi over 4 up top. Then 3 pi over 4. Then 4 pi over 4 there. 5, 6, and 7, all pi over 4. Notice, all of those are telling us those same things. Now, if you're reducing as you go, you wouldn't have had to go back and do this next step, but we didn't reduce as we went, so we look for any of them that we can reduce. Well, I can reduce that one. Okay, going around, I can reduce both of those. They both reduce to the same thing, which also helps us know that we did it correctly. Both of those reduce to just be pi over 2. 4 pi over 6 reduces to be 2 pi over 3. This doesn't reduce. This doesn't reduce. These do. Those just reduce to be pi, and so on. We just keep going through and doing that. Notice, there's all those same kind of patterns that we've talked about before present with our radians as well. So find the patterns that make the most sense to you and then use those. So then to practice this idea, I'm going to give you a sheet here and we're going to see how you can fill it in from memory. It's going to include degrees, radians, sine, and cosine values. So put away your notes or turn them upside down so you can't see them, and then fill in the picture.